Yes, good evening all. So myself, I am Ravi Teja. I
Sir,
am an
just wait a second, sir.
sure, sure. Okay.
Good evening, everyone. I am very honored to introduce today's our second speaker, Sri P. Raviteja Garu. He is working as Senior Technical Lead in V Micron, Hyderabad. He is having more than 10 years of experience in semiconductor industry. Now, I am handovering this session to Raviteja Garu.
Yeah. Yes. So I, before starting, I want to know, does everyone familiar with what is layout?
Actually, we know the layout diagrams for different logic gates and also.
Okay. Logic gates. Okay. So yeah, while I am studying in engineering, I think I studied on 300 nanometer or some 500 nanometer maybe. So you are having idea on stick diagrams and then basic logic gates and this color coding and whatever. So you have some idea about layout, right?
Yes, yes, sir.
I mean, eh, oh yeah, I'm trying to share the screen. Okay. Okay, can you see my screen?
Yes, sir.
Okay. So today I want to take session on like layout. What is layout and the flow, like what the things we will cover while doing layout. Uh, what are the things we will do, like verification and all those stuff. So first, what is a layout? So okay, generally how I will start is there will be three major things while we are doing any chip. Okay, one is design, and then the other thing is layout, and then the third thing is fabrication. Okay. A design will be done by some schematic designers, and then there is front end, back end, VHDL, Verilog coding, and then RTL census verification, and all those things will be there in this field. But the major things to simply understand, we do have schematic design, and then layout design, and then manufacturing. So what the layout guys will do is we will uh, simply represent the schematic in some pictorial representation, and the same whatever the layout we have drawn is fabricated as it is by the foundries in the sense TSMC or global foundries or whatever. Okay. uh, so that is what a layout is. It is simply, it's a pictorial representation of an IC. Okay. And then coming to a layout, we have digital layout we will call as mixed signal layout, or one is like digital layout and then analog layout. Digital layout, uh, in the sense it treats circuit stimulus as series of discrete logic ones and logic zeros over time. A logic one is typically represented as supply, and then logic zero is simply, it is like ground or the or absence of voltage, whatever it is. Okay. And then analog layout, design in the context of integrated circuit design is a discipline that focuses on the creation of circuits that operate in and are optimized for continuous time behavior. uh, what analog layout is, you will have information throughout the signal, that is analog layout, and then digital layout we will have information through ones and zeros. I mean, okay. And then, yeah, in digital layout, how we will do layout is, uh, digital, generally we will have time margin. Yeah, how we can say is, sorry, I will do one thing. Rather than saying this way, I will share one PowerPoint. Maybe that is, or not PowerPoint, Paint. Okay. Can you see my screen?
Yes, sir.
Yes. Okay. So, in a digital, we have, if I take my, I am operating like VDD as 5 volts, and then VSS as 0. So, anything between 0 to 1.5 volts, okay, my output will be, okay, if I take some CMOS logic. So if I give, what happens if I give 0 here? What is the output here for a CMOS circuit? What is the output here if I give 0? Okay, if my VDD is 5 volts, can anyone tell this? Uh, Hello? Um, Okay, okay. Now, so if I give 0 volts, okay, to this gate, what is the output I will get here at, at the drain? Okay, output will be 5 volts here. Okay, because if I give 0 volts, PMOS will turn on, and whatever the voltage is here, we will see at the drain. Okay, now the thing is, in digital, not only 0, but we will have some margin. Like if I give 0 to 1.5 volts also, okay, we will get this 5 volts. So this is called as noise margin. So this 1.5 volts is margin, but in analog l- circuits we don't have that margin. If I take a sine wave of like any 360 degrees sine wave, we have information everywhere along this wave. Okay, so if there is any noise here, this information is corrupted. So what I will say is, in digital, we have noise margin, and then the criticality in digital is low compared to analog. Analog layout is very critical. That's what I want to say. So, and now, yeah, standard cell layout. So for digital cells, we follow this standard cell layout. And yeah, so you, uh, sorry, everyone know what is like a stick diagram. So yeah. So yeah, for any okay, for this one, for a basic inverter, the stick diagram is this one, right? So this is like VDD, VSS, and then this is source, NMOS source, and then these are NMOS gates, and then this is out. Okay, and then sorry, there is gate. Yeah, so there is gate here. So this is the stick diagram for a standard, I mean inverter. So if I go to standard cell layout, generally for how we will build is all the logic gates or flip flops or latches, whatever it is, we will build in a standard height across the design. So this is very important while building the layout. Okay, the height is same for a inverter or OR gate or NAND gate or any flip flop. Okay, whatever it is, we will build in a same height, maybe like 2 micrometers, same height in the sense. So I showed you, right, this. Okay, this stick diagram. So if I take the height as 2 micron, okay, from VDD to VSS, if the height is 2 micron, we will build all the gates, like whatever the gate is or whatever the distal block is, like NAND gate or pass gate or whatever, we will build in the same 2 micron height for entire design. I mean, if I making some 28 nanometer SerDes, okay, or 28 nanometer DRAM memory cell, okay, for this entire DRAM, I will use only this 2 micron as standard height. Uh, and the reason for that is reuse. So if I take any digital layout, we will use, if I take have if I have some AND gate or NOR gate or pass gate, whatever, or some deeply flow or some latch, whatever. So all those we will use like almost thousands of times in a DRAM cell. If I take one DRAM memory cell, I will use some hundreds of times the same cell. So if I have different heights e- for each and every cell, then my area is wasted, and then I cannot optimize save area, or I cannot do an optimized layout. So for that reason, yes, I will do standard. I mean distal cell in a standard height. Sorry, standard height in the sense. So imagine I'm using a circuit of some inverters, and then I have some NAND gate, and then I have some mugs here, and then this is going to some, like I have some combinational logic circuit here. Okay, so if I have height of 2 microns for this and 1 micron for this, because the transistors are low, right, in inverter compared to some mugs or some D flip flop or latch or whatever. For inverter, it is having only two transistors. Okay, so I can do this in smaller height. I can do. So if I do this in 1 micron, and then if I use for NAND gate 2 micron and this one like 2.5, what happens is I cannot place all these cells in a single power grid. Okay, a single tap. We'll call them as tap. Okay, I cannot place these cells here. Now what I will do is, by making this in a some standard height, 2 micron height, I can keep uh, so here inverted. Okay, and then I can keep NAND, I can keep flip flop, I can keep latch, and then XOR, basket, whatever I can keep in this same height. Okay, in this 2 micron height. So here I am saving lot of area, and then imagine if I make one thing in 1 micron and other thing in 2 micron. So you are not only wasting area, we are also like increasing some so routing resistance or cap or parasitics from this thing to like from inverter to here. So you need to like route in a different way. Here the routes are like very straight, but here if you are having some different heights or something, you need to route in a different way. That will increase your parasitics, and then you will have some timing issues or whatever, many issues. Okay, so so that's what a standard cell layout is. Okay, the height is fixed. So yes, this is one thing, and then the other thing is like performance optimization. Just to, what happens is if you build, okay, if you are using some 5 6 AND gates and you're using different sizes for different blocks, okay, then what happens is one AND gate will have some separate circuit behavior and layout parasitics, and the other one will have a different parasitics. Okay, but what the designer will assume is, so generally why while they are doing some transistor modeling, okay, while they are doing some transistor modeling, every designer will have, if I take a PMOS here, okay, this is PMOS, so source and drain, okay. So what happens is every designer will have capacitance readings are for this. This is called transistor modeling, like source to drain cap, sorry, source to gate cap, okay, source to gate cap and gate to drain cap and everything. They will have this modeling, okay, and then they will start designing their schematic. The reason for this is if he want to design a circuit have having some like 1 gigabit, okay, output, okay, if he don't have this like transistor modeling information, okay, how can he design this high speed 1 gigabit signal? He can't do that, because only if we have this parasitic readings, then only he can design an appropriate circuit which can give us a like 1 gigabit of clock, or yeah, whatever. Okay, so transistor modeling is very important. Every time you don't say okay, and then yeah. So yeah, we are done. So this is about standard cell layout, or like almost all the digital cells, whatever digital cell you are using in your entire chip, we will maintain a single standard height. This is very important uh, thing for a layout engineer. This is very important thing. And then yeah, analog layout. So as I told you already, digital layout we have some timing, I mean noise margin like 1 to 1.5 volts or some 3.5 to 5.5 volts. Those 1.5 is some noise margin, but in analog we don't have any noise margin. So as we don't have a margin, definitely the criticality here is more in analog layout. Okay, so some examples of analog blocks are op-amp, band gaps, ADC analog to digital converters, DACs, regulators, uh, and everything. All these blocks are like analog blocks. So how we are implementing these layouts? Okay. Uh, so is everyone clear what I am saying? Or are you getting what I am saying? Hello, no response.
Yes, sir.
Sir,
We are getting you. Please continue.
Okay. If you have any doubt or something, you can stop and you can ask. Okay. Maybe I am not used to give sessions like to these many people. Uh, so yeah, I was some bit tense, but that's okay. Okay, so standard cell layout, I think I am clear in this standard cell. Then analog layout, if I come, so yeah, while doing any floor plan, like any implementing any layout, first we will concentrate on floor plan. Floor plan involves like the critical blocks. Generally, we will see what are the critical blocks in that. Okay, how I can say is I'll go to paint and I'll explain. So this is my block, which is having some, okay, I'll take some regulator here. Okay. So yeah, this is regulator and this is reference voltage and this is feedback voltage. Okay. I mean, this is a basic regulator. Then this is a feedback resistance. So this is a regulator. In this regulator, we have op amp, one op amp, and we have feedback resistance. Okay. And then there is output switch, which drains a use current here. And then output is connected to some again feedback resistors. Okay. And this will come to this. Okay. So this is Vref and this is feedback volt. So okay, my regulator output voltage, let's assume it is 0 0.9 volts, and then my reference is 0.6 volts, and then the feedback is 0.6. What this circuit saying is, okay, only whenever feedback is equal to your reference voltage, then you can get this 0.9 volts. Okay, that's what this circuit. Anytime if your feedback is either less or low, I mean either more or less, uh, based on this current draining by this device and then this resistor feedback circuit, uh, it will like set this to reference voltage. That's what this operation is. Okay, so what happens is circuit designer, what he will do is, uh, as we want a zero point 0.6 resistance here, so that means it should be like so okay, maybe let's assume that is this is 1 is to 2 ratio, and there is a drop of, okay, 2 is to 1, maybe there is a drop of, yeah, 0.6 volts here. Okay, so that means 0.6 volts come here and it will go here. Okay, now as a layout engineer, so this is what circuit designer will design and it will give, so he will give to us. Now what we need to make sure is, oh sorry, yeah, what we need to make sure is, we need to make sure that output is 0.9 volts, and then this reference and this feedback is matching from our side. We need to take care of this. For this to happen, as I told you, the resistors here is 1k and, oh sorry, If it is 0.9 volts, the drop here should be, yeah, 2k. This is 2k resistor, okay, and this is 1k resistor, so that it will be 0.6 volts. Okay, now what happens is there shouldn't be any extra resistance other than this. If you are having any extra resistance other than this, you can never get 0.6 volts here. This circuit is designed in such a way that uh, if you draw layout exactly how schematic designer has given, only then it will work. If not, there will be uh, mismatch between reference voltage and feedback voltage. Okay, that means we shouldn't add any. So we need to know that here this resistance, feedback resistance is important, and there are other things. The op amp, so op amp here is very important, and then the switch here is very important. Okay, let's for now we can talk about this feedback resistance. So if I have any extra routing here, okay, any routing here, this entire path is a resistor, right? This entire metal is a resistor. So that means this entire metal is a resistor. On an ideal case, we have designed in such a way that if it is 2k resistor, okay, then the drop will be 0.6 volts and the feedback will be 0.6 volts. But as you are adding this routing resistance here, now the, instead of 2k resistance, and then if you are adding some 200 ohms resistance, okay, routing resistance, that means it is becoming 2.2k, right? If it is 2.2k, then it can never be, the feedback can never be 0.6, okay, 0.6 volts. That means this regulator will never work. So as a layout engineer, you should know that you need to place these resistors, okay, in such a way that it should be very closer to this to this input inverting terminal. We'll call this as inverting terminal. It should be very near so that the resistance can be reduced. You might think that if it is 2k resistance, okay, then definitely, even though if I keep it close, there will be some resistance added in this metal of some 50 ohms or so, okay, then it will be a problem, right? You might think in that way, but what schematic designer will do is every time he will add some parasitic thing. I mean, he will design a schematic. Every schematic designer will design his circuit with some margins. Okay, if it is like 1.95k to 2.05k, also the feedback will be 0.6 volts in such a way that we will design the circuits in such a way. Okay, so it's okay to add a minimum. So there is no any ideal case of a layout, but you should be intelligent enough to, you know, core plan to reduce this resistance, feedback resistance. That's what we call as floor plan. Okay. Yeah, that is, and yeah, transistor and component placement. And again, the floor plan involves some resistors and then voltage, some voltage reference, current sources, and everything will be there in this floor plan. Current sources in the sense, if I take any block here, okay, again, and then if I have some block here, if I am like biasing this block using this current mirror, okay, current mirror with some 100 micron current. Now what happens is, so every So every wire is a resistor. Okay, every wire has some lumped elements. So we will call lumped in the sense this inductance, resistor, and cap. Every wire has this inductor. It will have some field electromagnetic induction, and then there is sorry this is and then there is some resistance added to this. Because of this voltage drops, electron should travel from here to here. That means it is losing its velocity. That's called as drop. And then there is a capacitor. Okay, capacitor in the sense, if there is any parallelly running metals are there, then it is a plate and this is a plate, right? Then there is some field induced between these two. Okay, so that we'll call as capacitor. So that means this 100 bias, if it is generating some 100 micron current, and if it is training this block, it should be 100 micron here. Okay, so when you are for planning, okay, if you keep this block here and if you keep this block somewhere here, okay, then what happens is this block, you should route this 100 microns of current to the entire region. So you are adding this much of resistance again, and then there is some field cap or whatever. Okay, so yeah, here you are adding some, imagine some 200 or again 300 ohms of resistance. That means by the time this 100 micron current reaching here, it will be some 90 or 80. Okay, so that means your output, you will not get the desired output. Okay, because your input current is reduced, so the output will be reduced. So that's what, as a so as a layout engineer, what we will do is we will check this like critical, and we will check this current nodes, and then what we will do is we will place this block in such a way that it is very close, uh, close, and then if it is current net, we will try to reduce resistance on this or drop on this nets. So yeah, that's what we will do. That's what these all things will come into foreplay. Oh, sorry, this unit, you shouldn't say this. Okay, and then routing. Uh, routing in the sense again, like yeah, schematic, and then you will launch devices, and we need to route everything. Just wiring, connect to blocks or transistor to transistors, whatever. That is called routing. And then power grid. Power grid, again, it says like uh, power grid in the sense, if I have some multiple blocks, this, and this in my layout. Okay, so I need to draw power grid again in such a way that all these blocks should have enough, should like take enough current. That way my power grid should be. Okay, you need to plan this in a better way. There will be many things like some blocks will be, you might think these are like why you are wasting this area, but what we will do is if some blocks are not critical, say current critical, or some digital blocks, we will place these blocks here. But if some blocks are very high current, if they are draining some high load, okay, then we will place directly underneath the power grid. Yeah, that's what we will plan. That's what your power grid is. And then yeah, matching. This is, I think, when if we are choosing to come to layout field, so this is very important. Matching is very important because every interviewer will ask you this question, like what is matching in analog layout. And yeah, you can you need to know this, what is what all this stuff, process voltage and temperature variations. So okay, matching in analog layout. So matching is done to avoid process voltage and temperature variations. Process in the sense the fabrication thing, and voltage in the sense okay, again, while you so okay, okay, so this is matching process voltage and temperature variations. So process in the sense, imagine if I am having a differential pair here. Okay, oh, I need to tell this. So what is an op amp? Can anyone tell me what is an op amp? I want someone to speak, please, because if everyone is silent,
Yeah. So op-amp is one multi-stage amplifier that will require more than two or three stages of single-stage amplifiers in cascade mostly. So there will be differential pair. Then last stage will be power amplifier kind of emitter follower will be there.
uh, okay, what is an amplifier? Okay, if it is not operation, what is an amplifier?
So amplifier will be amplifying some signals. If some signal due to during the transmission it will lose some power. So using amplifier we can gain its power. Maybe voltage, maybe
Okay,
current.
fine.
Yeah.
Yeah, so okay, fine. Yeah, you're good. Thank you for answering. Okay, whatever. So what amplifier will do is, I will tell you in a simple terms. If you give some sine wave, okay, of uh okay, this, imagine this peak to peak voltage is 0 point some 0.1 volt or so, and then if my op amp gain factor is 100, okay, then my op amp output is 100 into input, right? A basic op amp, that means 100 into 0.01, that is 1 volt, okay. Or if my peak to peak voltage is 1 volt, 100 into 1, it is 100 volts, okay. That's what your amplifier is doing. That means if you are giving any small signal, okay, at the input, we will get an amplified output, which is multiple of the gain factor, either inverting or non-inverting. You will get two outputs. One is non-inverting and then inverting. So these two we will get. Okay, whatever output we want, we will use it. This is what op amp basic operation is. This okay. Now, oh, now what happens is that means, so op amp. So if I draw a schematic for this, so this is what op amp is. As a refer whatever. Okay, VSS. So VDD. So this is what an like op amp is. So this is V in one, V in two, and these are out one and out two. Okay. So what happens here is, so suppose your input is some peak to peak voltage here 1 volt. Okay. Then my gain is gain factor is 100 for this. Okay. Then my output here is So if this is like non-inverting, then the output we here will be inverting. Okay, of 100 volts. So peak to peak will be 100 volts. So this is what my op amp is. Now what happens is, if there is, so in the ideal case, okay, there should, to get this voltage 100 volts, or to get this sine wave, we should design a layout in such a way that there shouldn't be any noise added on this net. Okay, this is the important thing is this one. Okay, so okay, if this is inverting, that is non-inverting, and this is inverting. Okay, so if there is any noise, okay, on this net, that means if there is some 0.01 or zero point 0.1 volt of noise, okay, on this net, on your input net, means the output will be 100 into 0.01, sorry, 100 into 0.1, that is 10 volts. Okay, so the output here is, we are seeing 110 volts, but in the ideal case we want only 100 volts, but we are seeing extra 10 volts. 10 volts in an analog circuit is huge amount. Okay, so any small variation or any, generally, as for round figures, I am taking the zero point 0.1 or 100 volts, but it will be in the order of 0.01, or in this way it will be. So yeah, so any noise, if you introduce in either of this net or either of this net, okay, the it is amplified at the output, so we need to avoid that noise. Or there is one more thing, if you want to, if you add any noise here, okay, op amp has, op amp function is, it will cancel the noise between v in 1 minus v in 2. Okay, or we will call this as common mode rejection ratio. That is too technical, but generally speaking, what happens is, um, so I will not draw entire op amp, I will draw only differential pair. So I don't want any noise on these nets, uh, in the on these nets, or if I have added any noise in this, I need to add the same amount of noise here. Then both the noise will be cancelled and output will be the desired one, what we are, like what we want. Okay, either of the thing we need to do. For that you need to match parasitics, you need to match everything. Okay, all the things which are in, like, all the parasitics like resistance, capacitance, and everything, like device placement and everything. If I take this as A and if I take this as B, so A and B should be matched perfectly. Okay, only then we will get uh, the desired output. So here in an op amp, by this what we can understand is, in an op amp, differential pair is very critical. Okay, this is what differential pair. And then we have current mirror, which the current is draining here. Even it is critical, because whatever signal, okay, coming from here to here, it should drain properly. If not, again it will impact our outputs here. Okay, so the current mirror and differential pair are the two most critical things in analog layout. So wherever you are doing analog layout, if you see these two, like devices, one is differential pair and then current mirror, then you should follow blindly matching. Okay, that's what this matching is for. As I told you, common centroid. Okay, we have two types of matching. One is common centroid, and other is interdistation. Common centroid, we will do this for differential pair, as I told you, the first one, and interdistation, we will do this for uh, current mirrors. Wherever you see current mirrors, we will do this interdistation. So, what common centroid is? The centroid will be so if we have A is equal to or 2 and B is equal to 2 devices. Okay, we will use two different matchings here. We can use A B B A, or we can use A B B A. We can use either of these two. Okay, now this is this is called common centroid because the centroid will be common for all the devices. It is minus, okay, it is plus, it is in the plus side and it is in the minus side. So what happens is, I told you, right, process variations. Okay, if my etching is if at the time of fabrication, if the etching is from this side, okay, what happens is uh, the amount of etching variations on A will be same on B. Okay, the major uh, consideration is this. As I told you, process voltage and temperature variations, right? This is the process variation. However it is, so my if my etching is from the top, okay, so in that case also you will have same effect on A and B. Imagine if I put A here and B here, okay, so in other case if I put A here and B here, then if my etching is from top, then A is affecting more compared to B. There might be some difference, okay, from A compared to B. So to avoid this, what we will do is we will make this common centroid common for all the devices, whatever it is. If it is 8 devices, okay, then it will be A B B A A B B A B B A. So and then B A B. So from top you will have four A's, four B's. From right you will have one A, one B, and then from one axis we'll have A B B A. That means two B's and two A's. One has, and also one more thing is, if it is minus four, okay, minus 3, minus 2, minus 1, which means minus 4 and minus 1 is minus 5, and minus 3 and minus 2 is again minus 5. That means the amount of etching variation is same here. This is called uh, process. Okay, in terms of process we need to take care of this thing. Maybe, yeah, I need to close it a little bit fast. So the second thing is voltage. Voltage again, how I can say is, if I have A, again B, B, A. So if I take a wafer silicon fabrication, I didn't touch this topic of fabrication because what I assume is fabrication of an IC is very clear. Even in the textbooks also it is very clear. Uh, so I didn't concentrated on this. I went to direct matching or whatever analog layout. I went there directly, some circuits. So whatever. Oh, so what happened is, while we are fabricating, if I take a wafer, okay, and then some imagine we are doing some ion implantation, okay, on this. What happens is throughout the wafer, the ion implantation will not be the same. Okay, so here it will be different, here it will be different here. So it will be changed from center to, if I take some this edge, the implantation may varies. Okay, here it might be more, mm, 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 like more ions, and here it will be less, or it is not uniform. Okay, as it is not uniform, you cannot simply place a match device. If I have some four devices of like common centroid devices, okay, here four A's here. If I place one A here and then other A somewhere here, okay, and you place some devices in between. Now what happens is, here the ion implantation is different and here the ion implantation is different. Both are not, the gradient throughout this wafer is not same. That means there is might be a chance that this device may turn on quickly because of some VT variations, as we have more ions here, okay, more minority charge particles here, okay, which is required to turn on the channel. Okay, so this device will turn on quick and this device will turn slow. But in the actual operation, what we need is all these devices to turn on at the same time. I mean, due to some VT variations. Okay, what is happening is one device is turning on early and the other device is turning on late. So what happens is, uh, how I can say is, okay, now again it will impact our amplitude of this signal. Okay, the same way for whatever, for B or whatever. So this is called VT variations, voltage or VT variations. Okay, so in a matching circuit, you need to place devices closer, all the devices closer. So that is most important thing, to match our VTs. All the VTs should be matched, and particularly in current mirror, okay, you need to match all these VTs. VT should be so current mirror is this, right? Gate is common to all the devices, so VT should be common. Only then the ID saturations will be same. Okay, so that's what VT. And again temperature variations, process voltage and temperature. If what temperature is, again, if I take a metal, if I take a metal, okay, and if I take a semiconductor, okay, semiconductor, metal has negative temperature coefficient. The thing is, your if this metal, if we increase this temperature in the, if there is any increase in the temperature of this metal, okay, then the current carrying capability of this metal will be reduced. Okay, but in semiconductor it will be reverse. If the temperature in this is increased, then the current carrying capability will be increased. That means, that means your transistor operation dependent on the temperature. Okay, temperature. So by this what we can understand is, again, if we have some centroid device, okay, A and B, you cannot simply place here A and somewhere B, and then near to B if there is some inductor, okay, also inductor will have extremely high currents. That means more temperature around this thing, which means the this device will the speed of this device will be increased and it will be slow. For this reason, what we need to do is, to avoid this temperature effects, we will place matched devices as close as possible. So to avoid process, you understand, hope you understand, voltage you understand, and temperature you understand. So the temperature throughout these devices should be same. If not, again the device characteristics will be changed. Oh, yeah, that's what is. Yeah, that's what is matching. So in matching, we have common centroid. As I told you, we will use this for common centroid. We will be using this for differential pair, and interday station. We are using this for current mirrors. And then yeah, if I come to verification, we have I these are like few verification flows. The I mean almost all verification, all the companies will use this. And then there are many other verification checks. It will vary based on the product requirement or the organization requirement. Okay, but generally we will do all these things. Okay, LVS, DRC, antenna, density, latcher, PMIR. So LVS will call as layout versus schematic. That means if I have some schematic, this is schematic, and I need to uh, do this layout exactly. I need to match. I mean, I need to route exactly same as the schematic. Okay, with this layout. Now, once you feel that all the routings are done, you will run this LVS check, verification check, layout versus schematic. What this check will do is it will convert layout to GDS, okay, and schematic to netlist. Then it will compare both GDS and netlist. Now, if you miss any connection, or if you miss any pins or input output pins, or if there is any soft check, substrate issues or anything, whatever it is, it will LVS will give us throw us error. Okay, we need to fix those errors. That's what LVS is. Understood? Hope you understood. And then DRC is design rule check. So every founder, while you are doing layout, mm, so while you are doing layout, so we have PDK. This is called process design kit, which means foundry will have certain rules. Whatever foundry it is, okay, whether it is TSMC, Intel, or UMC, SMIC, whatever, every foundry has Micron. Every foundry has their own set of rules for every technology, whether if it is 28, 45, or 60, whatever. Okay, you need to do layout by following all those rules, whatever it is in PDK. Suppose your metal one width, if I take some metal one, okay, if that minimum width is 0.5 volts, okay, sorry, 0.5 micron, you need this is minimum, you need to draw metal one width of 0.5 micron. If you draw 0.4 micron, then this DRC will throw an error saying that the minimum metal width is 0.5, but you have used 0.4. Okay, so you need to correct this. That's what DRC is. Simply it will check like process design kit, and then it will throw the errors. Then we need to correct these errors. That's what DRC is. And then we have antenna violation. Antenna in the sense if there is any metal. Okay. if there is any metal, okay, connected to the gate, long metal, then at the time of manufacturing, or what happens is, uh, while etching, there is some charge, there is some charge stored on this metal, okay. Let's imagine this is M3, okay. M3 is connected to this gate, and whatever charge stored on this metal, accumulated, not stored, accumulated on this metal, okay, will try to discharge through this gate. This high amount of currents discharging through gate will like damage this gate oxide. Oh, that's what antenna violation is. That means this gate will act as like antenna, by which will try to pull all this charge accumulated on this metal, and then the gate oxide will be damaged. Okay, that's what the antenna violation is. Okay. uh, are you guys following?
Yes.
Can anyone explain me what is antenna violation?
Antenna violation, actually, this is new to me. DRC always that thing. Actually, I used mentor graphics long back. So DRC always it was there, but antenna I am learning new.
Okay, okay, fine. uh, okay, generally antenna is everywhere. um, Maybe DRC and LVS is like, while at the time of training, when you joined as a fresher in institutes, okay, you will have these things. I mean, you guys, like many of the like institutes will only give access to this LVS and DRC. So what happens is, okay, first of all, go. It's not technical. How to say is, if I take a software Java, okay, and if I take VLSI, okay, now the thing is, we will call this as software. Many people, once engineering is done, okay, they will say what job you're doing. They will say software, either developers or quality QA, quality assurance team, testing manual, or whatever automation. There will be many things. Okay, this is software, and then yeah, VLSI. We have design, layout, verification, and then yes, RTL coding, VHDL coding, and everything. Okay, we have these things. Now, what happens is in VLSA, as I told you, DRC, right? For for DRC to run, we need to have some verification tool, right? That tool is, one is Caliber. If you, I don't know whether you heard this
Yes,
name or
yes,
not.
caliber. Yeah, yeah, yeah. Yeah.
Okay, it is
Oh.
Caliber. One thing is Caliber, and Caliber is so one thing is Caliber, and there is one more thing, custom compiler, Synopsys custom compiler. It will have like, uh, we will call as like RV, or some, yeah, RV or PV, we will call them. This is one thing. This is Caliber is from Cadence, and then this is one thing is from custom compiler. Custom compiler is Synopsys tool. Okay. Now every tool, whatever tool it is, if I take a caliber of LVS DRC, this license itself, a single license costs 1 crore. Okay, 1 crore will be for LVS DRC. I mean, this is an around figure. What I'm saying is, it will be of like hundreds of lakhs to purchase this single license. Okay, but if you want a pure Java software, it will be in the order of lakhs. Okay, like 5 lakhs, 10 lakhs, or some for 3 months. Or there is in the market, you have multiple versions of, copy versions where you can get free and it will almost work equal to the original version, but there is no any tool which will work as caliber. Understood, right? Now from here what we can say is, if you go for a software training, a Java training, that is the reason they will charge you like 10K or 15K for 3 months, because their license are either free, or if they are using any licensed version, legal license version, they're paying just 10 lakhs or 15 lakhs, which will have 1 year. Okay, for 1 year. But for layout guys or for VLSI guys, the for the tool cost itself is like you are paying for a verification tool. You are for layout license. With layout license is virtuoso license. Okay, again this is a separate cost. So for all this setup, you are paying some 4 or 5 crores. Okay, or some 1 2 crores. Imagine. So that means if you want to go to a training institute, the training institute, if they are training you on a real time caliber virtues or whatever, they need to spend this much of amount to purchase this tool, and they need to train the engineers. Okay, fresh engineers. So here that is not the case. That is the reason what happens is, that's the reason VLSA training costs more. If anyone of your friends, or maybe I don't know, relatives, or maybe you went to this training, VLSA costs any in India or Bangalore, in Hyderabad we have Moschip. Okay, VLSA Institute. This is the best institute, one of the known institute. I shouldn't say best, known because other guys might feel, but one of the most known institute. It will charge for layout itself 1 lakh for 4 months. Okay, 1 lakh for 4 months. But here it is not that case. In software, it is like 5K or 10K. The reason is because of this tool cost. Okay, and then I had Raja saying about these freshers. Okay, why in VLSI field? Okay, for freshers, again, if we want to train them, okay, we need to again, a company should take this license free. Okay, company will already have this caliber which you saw license or whatever, will have 10, 15, 20, 40, whatever. Okay, so if I am training like 5 6 freshers, I need to use like 2 or 3 licenses for this. That means 1 crore, 2 crore, or 3 crore. Again, they need to spend for first 1 year. So that is the reason. What happens is, they are very particular uh, in taking freshers. They are very particular. You might think that without freshers, there is no experience, but there are other things nowadays. What many companies, what they are doing is, they are tying up with some. If you heard about Veda IIT, or again Moship in Bangalore, we have RVVLSI. Like what they are doing is, they are tying up. Companies are tying up with these institutes. They are paying some amount to them. Okay, and then they are hiring freshers, engineering graduates. Okay, and then they are joining all these guys to these institutes. Okay, then these institutes will train them. Okay, and they will pass back to this company. This is what major this is what going on in the market, mainly. Or else uh, they will bring from engineers from, for analog design. They will bring engineers from IIT, NITs, or bits or whatever. From there they will bring but for layout verification, yeah, from engineering graduates with a trained. Again, the thing is, again, Without any certified training, you cannot enter into the field. I just want to see, going these technical things you might get bored. So I just want to tell you about how industry is, how you need to get, how if you want to guide people. So you need to tell them, you need to understand how the things. If you want to take verification training or PD physical design, so you know right what verification is. Maybe or the previous one Raja has explained this. So if you want to take any of this training, you need to spend some amount. And what I can say is, this is best field in not only India, everywhere. If you go wherever in this world, VLSI is one of the topmost field, topmost paid. I don't know how much information you has. While I am studying engineering, I don't luckily my uncle is a VLSI engineer in Intel. So he guided me here. So yeah, I have some information on this. Later, I have like almost 10 to 15 friends of my engineering whom I feel they are like very better, and then I pulled them from software to VLSA. Why I want to say this is, in India going forward, if you see this news, we are right now we have Micron fabs in India, in Gujarat, with Tata. Tata and Micron is building some fabs, and then of post COVID things have been changed drastically. I don't know how much information you has, but post COVID things has been changed completely. Almost all the companies, many companies are moving out of China. China is the manufacturing hub. It will provide almost 80% of world is dependent on China. Now that has came to some 50%. So 45 to 50, I mean within just like 3 4 years, their 30% of stakeholders from China has moved out. And almost in this 30%, 80%, like Apple is the main one. Apple is creating 4 lakh jobs in India. And then we are having this Vivo is coming. And then there is Amazon, and then there is Google. So the biggest companies in the world is coming to India. So without IC, there is nothing. What I can say is, everywhere VLSI is needed everywhere. I mean, everything now. Future is all about electronics. Okay, if you take a car, okay, uh, if I take a present car, if you so every car has this ADAS features, right? Recently, you will see this car MG Hector, Internet Inside. A lot of times we will see internet and inside means it, that means it should have some chip. Without chip there is nothing. That means with it should be a VLSI thing. It should be, everyone should involve, design, layout, verification, everyone should involve. On an average, if I take some course in India, some 1 to 2 lakhs of course per month is like like the sale is that. So that means car, this is automotive, and then now it is like IoT in the sense, uh, if you enter the office, maybe you have seen, right, automatic light system or whatever, uh, everything now is automated, and for that automated we need a chip. Okay, now entire many of the countries are focusing. India is giving the most of the libraries from India, whether it is verification engineers. If I take my company, okay, Micron has in 2019, okay, Micron started in Hyderabad and with some 40 to 50 members. Of course, Micron is one of the biggest company in the world. It is like second in DRAM. Entire DRAM or memory. You will see Apple products are Micron products. Okay, whatever. Now in 2020 it is 50. Within now 2025. Okay, next we are around 6,000 members in Hyderabad itself. See how much. Can you imagine a company goes from 50 to 6,000 employees within just 5 years of time? Imagine that is the scale they are increasing. Now, keep on the hiring is going on. Hiring is going on. We are looking for the best available engineers. We are always looking for. So that's what is happening outside. In India, we have lot of uh, opportunities, and why I am saying all this stuff is I want every professor to educate their students on importance of VLSA. They will get best in the field salary. So I don't want to discuss too much about salary, but yeah, definitely financially you can't get better than. You will sometimes see, many times you will see that an IIT employee in newspaper you will see that an IIT employee, okay, from some IIT Kharagpur employee got some 30 lakhs of package, 40 lakhs of package. Okay, 2 crores, 1 crore leave them. Okay, that is like too much. But on an average, even 30 lakhs are some of my family members or my brothers. We will listen this 30 lakhs for a software employee, right? So a lot of time. Oh, sorry. Please give me a minute. So we will, yeah, we will, yeah, a lot of times we'll go with all this. What I can say is for a VLSA employee, okay, if he is having he need not study an IIT. If he study a normal engineering college like our like which are in imagine if it is Paida. I studied in Paida, Vishakhapatnam. So right now it is not there, but yeah, Gayatri, Gaitams, whatever, okay, Vignan. So he can also get for if he is having like 4 to 5 years of experience, he can also get like 30 to 40 lakhs. So this is the what industry is paying, because the reason is in America, analog layout designer is the highest, second paid after president. So this is the thing outside. So they need to pay huge amounts if it is China, Taiwan has TSMC, and then Germany, UK, United Kingdom, wherever there is layout. I am talking about layout or verification, whatever. Okay, they need to pay huge amounts there, but in India they are paying very less. And then Indian, right, Indian mindset is like they can work extra, they can finish more tasks. So yeah, that's the reason world is saying like here India is the better choice for them. If they are moving out of China, they need more young generation, more people very who are ready to work, or like more enthusiastic generation is. So what they have found is India is the better place. So I request everyone to like educate our students the importance of VLSA. I think this any of us can help you help to guide students, or if they need if you find. So what happens is, I want to tell one example. One of my friend is like Srinivas. Okay, his name is Srinivas. He studied in Pragati College. In Pragati College, in BTech he got 91 percentage. Okay, uh, I mean he is school topper in 10th. Then he got interview. He selected an interview in IBM, and then IBM has paid him 6 lakhs. It is in 2014. I am 2014 batch. So uh, he he got some 6 lakhs of package in 2014. 6 lakhs is more for us. So he joined there. And then I joined in VLSI for 10K. There I started for 10K. And then after 2 3 years, his like package is at 7 and mine is like around 11 12 or whatever. I am not saying we are great or something. The thing is, if he has a better, I used to feel for him like because he is like brilliant students starting from schooling. So I used to like brainwash him like, why you're wasting all the talent here, why you can come to VLSI. Now he came to VLSI in 2017, I think. So he resigned there, he went to Moship and then he trained there and he went to PD, physical design engineer. And he like now he is into VLSI field. Now what I want to say is, if you think your students are a lot of times you feel that some of your students will be like gems, so for them you need to guide them in a better way, like what is better for them, what is better future for them. I see nothing is less software is even a software, any every job is uh, like I am not degrading someone or I am not saying something. My intention here is, when you have a better opportunity, try for that, or at least you can we can motivate the bright students. Or there is no bright or something, but because I am an average student, I got just 68 or 69 in BTech. So right now I am here. So it is simply the mindset or the guidance. So I have a better guidance. So I request what I can why I am saying all this stuff is, at that in 2014 we don't have these many layout jobs. If you see, entire India we have some around 1000 or 2000 jobs. So there the competition and then getting job itself is like very hard at that time. But now a Micron itself has some 2000 layout templates, like 2020, and within 10 years things have been drastically changed. In India we have some biggest companies like Qualcomm, Nvidia, and we have Intel, and then we have Texas Instruments, Analog Devices. Many companies are there, many those are all product. Again, we have multiple services company services which will give you like better opportunities, better companies to work. So yeah, uh, this is how the industry is in India. Okay. Uh, Hopefully you are following this or no.
Yes, sir.
Oh yes, okay, fine. Yeah, thank you. So yeah, that's what a general thing. Hmm, I don't know to take maybe see what happens is, if I tell you the antenna violation, uh, I don't know to what extent you will get this, because okay, DRC and LVS is fine. Generally, even in even in engineering we will learn this, or some training institutes we will learn this. So I will go like. Not in depth, but like general terms, I will explain. Antenna, all these are layout checks. Once you finish the layout, you need to run all these checks and you need to make sure there are zero errors. Only then you can you can tell the designer that my layout is clean. One thing is antenna violation. As I told you, if any metal connected to the gate is long, which then there might be chance of antenna. In antenna check it will give that in this metal you might say antenna. For that you need to use like metal jumpers or reverse biased antenna diodes we will use. Okay, first I want to ask, uh, Is everyone aware of fabrication, IC fabrication?
Yes, sir.
Okay. Okay. You are aware of fabrication. Okay, good. So in fabrication, what happens is first we will build base layers. Okay. Base layers in the sense substrate and then source drain regions, gate, and then substrate contacts, and then we will build metals. Okay. So metal one, metal two. So that's how the fabrication is. So it will start from base and we will build metal one, two, three. So what happens is every time we are doing photolithography, okay, sorry, every time we are doing, when we do this photolithography, if I done this M1, if I fabricated this M1, before fabricating M2, what I will do is I will remove all the charge accumulated on this. That is called annealing process or cooling process. Okay. I will give some time to this metal to cool. Then I will start M2 fabrication. Okay. Again, I will give some time. Time in the sense whatever charge it is accumulated here, I will remove this charge. Okay. Understood, right? So we will build M1, M2, M3 by giving some time to settle down or to cool down. Now, if I have antenna violation on M3, okay, as I told you, we will use metal jumpers. We will call them, the technique to avoid antenna violation is metal jumpers. Okay. If there is any charge on this metal, so metal jumpers in the sense we need to chop some metal here and then we need to go for higher metal. Okay. Higher metal in the sense, as I told you, on my antenna is on M3, I will go for M4. Okay. That means I will chop here. I will go for M4. That way your antenna will be gone. Now, can anyone tell why I am not going to M2? Metal 2. Uh, Please try to be vocal so that, see, once you are answering some questions, it will be interesting for others to listen.
Can you repeat the question one more, please?
Okay, so yeah. So I have my antenna on M3. Okay. For antenna, what I told is, if I have any long metal this way, I will chop this region. Okay. I will chop this region and then I will use higher metal. So I will use this higher metal. So if it is M3, I will use M4. Okay. I have a choice. As I'm chopping this metal here, M3, I can use M2 also here. But I am using M4. What is the reason I am using M4 here rather than M2? Can someone try to answer this question? It will be interesting. For metal, as I told you, to avoid this antenna violation, we are using metal jumpers. Okay, metal jumpers.
Hello.
Yes.
One of the reasons that M4 is higher metal and it is having a larger width of comparatively M3, and because of that, the current, the resistive part of this M4 will be lesser as compared to M3. So this will create some uh, this effect of current, minimization of current effect. That's why we are taking M4. Maybe one of the reason.
Not exactly.
Yeah.
And thanks for answering. I want that. Anyone, please? You can tell whatever you want.
Sir, wires generally up to M15 layers are there even for cadence 180 nanometer. We can
Uh,
go for M1, M2, M2, M3, M3, M4 up to M14, M15.
mm.
Those are, can be called it as wires so to avoid the interference or whatever it may be overlapping or like that. So,
That's a different question.
okay.
Yes, from M3 to M5. If you are going from M3 to M15, yeah, we will call them VS. That's correct.
Okay.
Yeah,
Yeah, yeah.
but
Once again, question, sir, so that I can try for my level best.
okay. So I am having some antenna violation. What I
Okay,
told about antenna violation is if there is any charge accumulated on this,
okay,
if
sir.
there is any metal connected to gate, longer metal, then
Oh,
at the time of etching, manufacturing process, while
oh,
we are doing some annealing process, the amount of charge, the larger amount of charge stored in this metal will try to go through this gate.
okay.
So this current will damage this gate.
Yes,
So
yes.
that means once the fabrication is done, this is at the time of manufacturing. So while we deliver the layout, what we will think is this layout is good and we have delivered. But at the time of fabrication, it is gone. The gate is
Mm,
gone. In the reality, this transistor will not work and the chip is a failure chip, failed chip.
okay.
So this is what antenna effect is. That means the gate oxide is damaged. Now to
Okay.
avoid that, what I told is we are using. So if I have M3,
M3. Okay.
longer M3, I am not using M2 here. I am using M4 here.
Okay, sir. Okay.
I am going for M4. Now my question is why I am going for M4 instead of M2. I can use M2 also here. Metal
Okay.
jumper. I mean,
Okay.
I am chopping this area. Okay, I am chopping this area. Uh, so why I will chop is generally why I will chop is I want to create some open circuit and then I want to remove this charge before reaching to this gate. Okay, and
Okay.
then if I build some other after next metal, this charge will be gone.
Okay.
There
Okay.
won't be any charge left over. Now my question is when you have antenna on M3, you can go to M2 also, but you are going for M4. I am asking the reason why we are going for M4 instead of M2.
Resistivity variations taken place, sir. Maybe my side. Resistivity varies from M2 to M4. M4 maybe M4 is offering more resistivity compared to the M2. So that
Uh,
indirectly we are creating dielectric nature. No?
Not exactly.
Okay, sir. Okay, sir.
Yeah. Okay. Now at the time of fabrication, what do you think if I have metal 1 to metal 7? Okay. What is fabricated first here?
M1.
Okay. M1. Next.
M2.
Next.
M2, M2.
M2, M3, and M4, and so on, M7. That means
Correct.
M1 is fabricated at first and M7 is fabricated last. Okay. And also, this is first point. And also, I told once M1 is fabricated, before fabricating M2, what I will do is I will remove all the charge or heat. I will make this device cool. I will make this metal cool. I will remove all the charge on this metal. Only then I will fabricate M2, not without cooling this metal. Because what happens is if I have lot of heat on this and then lead heat on this, this complete heat may like may uh, in Telugu కరిగిపోవడం అంటారు కదా, సంథింగ్ that will happen because excessive heat,
Melting, sir.
melting, sorry, yeah, will make this metals melt. So to avoid that, what we will do is, first we will manufacture M1, cool down, and then M2, cool down, M3, and that way. Now by this point you can tell now why we are not going to M2, why we are going for M4. Okay, I will tell you the reason. The reason is, this is M3 and we are having antenna on this, right? If I go to M2, okay, now practically what's happening is, this is M3. First I have chopped M3, okay, this is M3. I chopped, and here I am going to M2, and then there is vias, M2, M3 via, M2, M3 via, okay. This is connected to the gate, okay. This is my gate. So what happened is, before manufacturing M3 itself, I have fabricated M2 here. Okay, right. As I told you, first M1 fabricated and then M2 is fabricating. Here now M2 is fabricated. Okay. Once after M2 fabricating, you are fabricating M3. Okay. That means you have closed circuit here, right? M2 is connecting to this M3. This M2 is M3 is connecting to M2, and the current is flowing to M2 and it is going to M3, and again it is discharging. That means if you use M2 here, okay, there is closed circuit. The circuit is closing here. That means there is a current path. The current is still discharging through this gate. Now if I use M4, okay, what happens is, this is M3, okay, you got, there is, okay, this is gate, okay, this is gate, this is M3, this is M4. Now there is no M2 here. Okay, so there is no M2 here, we are using M4 now. So now if there is any charge on this M3, okay, you can remove this M3 before fabricating M4, because this is an open circuit, there is no closed path, right? For this charge, okay, to travel this gate, okay, there is no path, because M3, M4 is not fabricated. You used M4 jumper right here. This is not fabricated. That means it is a open circuit, right? So whatever charge is there here, you are removing this. Okay. Now you are fabricating M4. Once M3 is fabricated and it is cooled down, now M4 fabricated. If there is any charge on this, okay, that doesn't matter because it is small area. And also now there is a closed circuit, but there is no charge on M3, because before fabricating M4, you removed all the charge what is in M3. Understood or not? Still you have doubts? Or okay, this session is recorded is what I had. So you can go through this explanation 1-2 times. Okay, you might have confusion at first, but definitely you will understand this. Okay. uh, Understood or not? Okay, I think the time is like around 10 here. I mean, there it would be 7:30, I think so. uh, Time is moving, so yeah, maybe you can go to that explanation and you can understand that. So my intention here is, when we are learning something, we should be very clear. Many people, I feel that they know antenna. If I ask them what is antenna violation, they will tell that if any long metal is connected to the gate and at the time of manufacturing due to excessive charge stored on that metal, it will try to destroy the gate and the metal oxide will be damaged. They know that. But if I ask them in an interview, if I question them, what you will do, and they will tell I'll use metal jumpers. And if I ask them same question, like why are you using, if I got M3, antenna on M3, and why I'm going for M4 instead of M2, means they can't answer that. So many people are theoretically, they are very good and clear, but we need to have some practical knowledge, because if I take uh, analog layout, okay, what I feel is this is the most easiest subject compared to verification, because Raja might be doing some verification in analog field, but if you come to digital, verification is the toughest verification. If you are doing from if you are doing verification for uh, a DRAM or DRAM design, if you are doing any verification, that is the toughest thing, because you need to have some JDEC specs, which where you need to buy heart around 800 to 900 of keys, which Samsung, Hynix, and then Micron entire world will follow a standard spec that we need to know, and all the layout verification engineer should know that. It depends on where verification depends on, but okay, it is not too difficult. It is very easy once you understand this flow, and once you started working here, you will come to know. But in layout, coming to layout, we will have only see some concepts, around 15 concepts. Okay, as I told you, maybe at first while I started the class, see, I'm very nervous, I'm tense, so maybe you guys may not follow what I have said, but from here, standard cell layout, you can go through the recording. Whatever told you is very clear, is what I am feeling. So we have very few concepts. Okay, if you learn all these concepts, layout is very easy. That's what I want to say. Okay, it is very easy to crack the interview. It is very easy once you enter this industry. It will be very easy for you to survive here. It is not any hard task. If you see for outside, you will see the stick diagrams, logic gates, and the biggest circuits, op amps, and then you will see some nodal mesh analysis and all those stuff you will see. But once you come here, what you will feel is, okay, this is not as tough as I am thinking. It is very easy, and I can easily understand. This is what you will think. So that's what my intention is. Okay. What I want to say is, whatever you are learning or whatever uh, you want to deliver, I want you to be very clear. If a single concept, if you are learning some antenna, or if you are learning some density, if you are learning some op amp, just focus little bit more, and then yeah, you will understand it better, is what I want to say. And then here, if I antenna is done, density is like every manufacturer fab will have this uh, some density violations, so minimum and maximum density. What exactly this is, if I take, okay, sorry, give me a minute. Oh, okay. Okay, maybe I think the time is up, and you guys are like from, I don't know from what time you are hearing these sessions. Sorry, I couldn't able to.
Yes, sir. Up to 6:30.
No, okay. Okay, fine. I couldn't able to cover this, so maybe if I have time, some other, if on some other day, I will try to cover all this stuff. Okay, but yeah, as I told you, see, this technical things. Why I didn't want all these things is if I tell you all this stuff, okay, my personal feeling is there is no point without first you need to understand what is industry and then how the industry works, and then you will enjoy this learning. If not, what you people think is like you will be bored. So that's what my intention is. First I want to explain you industry, then I want to go all this stuff. So that's what I have taken more time on explaining what how the things are unfolding in India going forward. Yeah, what I want to say is we have India has very bright future, especially in terms of VLSI. That's what I want to say. So please educate your students or your friends, kids, or family, whomever it is. Try to motivate them, and sometimes what happens is you might get the job finding might be little bit late. Okay, because as I told you, there will be some competition and the job amount of jobs are little bit less compared to software. It may take a little bit time, but once you enter this field, uh, entire generation can be settled. That's what I want to say. That's how the field will be. Okay. So mostly I have covered everything till here. These are like some deep and well, and then FinFET. FinFET is the latest nanometer. We will see right now. We will see right outside like movies, like or some everywhere. We will see nanotechnology, or then Qualcomm or iOS like chips, and everywhere we will see this FinFET technology. Right now, entire industry is running on this. So I just want to give some brief introductions. Only these things are left. Hope you will. Ah, yes. Sorry. Uh, I want everyone to listen this. So these are the references. Maybe you can suggest our students. So these three things, okay? Particularly Behajad Rajavi. I don't know how many people has heard about this name,
We
but
know, sir. We know, sir. Especially for analog IC design, we used to suggest to our students. We are running HANAR course as well as for MTech VLSI also, sir.
okay, thank you for answering that. Yeah, so I request every student should go with this. Every electronic student should go through this. There are 90 lectures. One is 45 and other is 45 on electronic. So he will start from material physics, like from basic inductor and then valence band, conduction and everything. He will see from orbit, nucleus, everything. He will start and he will end at some op-amp design. So he will clearly say it will take a lot of time. Sometimes you will get bored like repeating same thing, but this is very important thing. I request all the professors here to tell your students to go through this lecture, and also I would suggest you to go through these lectures for better understanding. And for analog layout, if there are any analog layout trainees or if anyone want to enter this, the book I suggest is Art of Analog. Not only every analog layout guy will say this book, Art of Analog Layout by Alan Hastings. This covers I like all the layout issues, what I told, like common centroid, deep submicron effects, and whatever. This is one thing. And analog layout and design. This is a YouTube channel. This is a direct YouTube channel. Okay. This is also very good for layout. So he will also cover entire layout. So like band gap, uh, from band gaps to analog layout, like matching standard cells or whatever. Okay, fabrication, everything he will cover. Uh, this is also very good lecture, and this is very easy to understand. Okay, maybe art of analog layout might be little bit difficult, but the best one. And yeah, Behjad Rajave is like, he will tell in such a way that you will enjoy these lectures for sure. I guarantee you, you will gain lot of knowledge if you went through all these 45 lectures. And I request all the fresher students or who want to enter to layout field or who completed their layout training and then they are finding it difficult to get the job. Okay, I would suggest them to like follow this channel. Okay, you can, after going through this, and if you write down and if you study completely thoroughly all this stuff, you can easily clear the interview. Okay, you can gain some knowledge. Okay, yeah, that's what. So thank you everyone for giving me this opportunity. Thank you,
Ravi sir,
my friend
participants are
Dilip.
asking about your email ID. Can you please share it in a chat box?
Yes, sure. Email ID. Okay. Oh, where is this chat box? Okay. Sorry. Yeah.
Participants start share his email ID in chat box. You can mail any queries or any technical assistance. You can mail.
Yeah. Any questions you can ask? Sorry.
If anybody have
Maybe I
any
have
question,
taken so much of your time, but yeah, hopefully this will help.
No, sir, no problem. It is more informative.
Yeah, thank you.
Bhakti sir.
Yeah, yeah, sure. Thank you. Thank you. Any questions? Is anyone having any questions? You can ask me. Any technical or any layout about layout or anything, if you want, you can ask. No questions. Thank you. Okay, thank you, everyone. I will sign off, and yeah,
sir,
what I want to say
wait a
is,
second, sir.
hmm, okay, one thing I want
You can
to
speak.
say is, if anyone has any doubt or if anyone want any help, so sometimes what happens is, any of your students are like little bit financially struggling, or any of the students you feel they are studying well but they don't have a correct guidance or anything, if you feel any of that, they can always contact me. I will try to help them from my side. And if anyone want any suggestion or any technical knowledge, maybe what happened is, see, I am giving this session, this is the first time I am giving to these many people. And then so I am right now in a business trip. I couldn't able to prepare this PPT. I'm very busy in work and all those stuff, so I'm little bit nervous at starting. Yeah. Maybe I'll try to plan any other session. I will discuss with Dilip and I will try to, yeah, plan any other session. But yeah, if
Sure,
you
sir.
have
We
any
will
doubts, you
contact.
can, yeah, always call me, or you can mail me. Okay. Anything. Thank you.
Teja sir, 1 second. Teja
Yes.
sir, thank you so much for accepting our invitation as a speaker for this FDP, sir. Surely we will encourage our students to go towards the VLSI companies. And you have started insightful applications in layout design, and you are very much given some techniques about how to design a layout and what is the necessity of parasitic considerations when designing a layout, and what is the use of DRC and all. It was very useful, and we will follow these cases in our practicals and all the things, sir. Thank you very much, sir.
Yeah, thank you. Thank you so much for giving
Thank you,
this
Ravi Teja
opportunity.
sir.
Yeah, thank you. Thank you, madam. Yeah.
Thank you all the participants. Be in the meeting. We have a valedictory session.
Okay, I can sign off, right?
You can sign off, sir. Thank you
Okay.
so much.
Yeah, thank you. Bye.
Madam, మీరేం present?
Sir, ఉన్నాను. Okay, sir.